the frequency response for the amplifier is usually look like this. So it has an starting frequency and ending frequency. So the amplifier is working in this range. Okay, so this is a lower frequency. This is a higher frequency. Usually when we calculate this higher and low frequency, because the amplitude, the amplification here, A, is 0.5 if you are talking about power ratio, or 0.7, where it is 0.707 if we are talking about voltage ratio. Okay, so if, for example, amplification is 10, okay, in the mid here, in the middle here, it is 10. If it is 5 here, for example, this is the F1, where we calculate F1 for power ratio. If it is 7.07, then this is where F1 exists for voltage ratio. Frequency response noise, as I said before, you see here we have at each frequency, this is a frequency. So for each frequency, you have amplitude that's different. So if you have a signal like this, okay, that has a lot of frequencies, it's not a sine wave, then the amplifier will multiply it by different numbers depending on the frequency. So for example, this frequency will be multiplied by this amplitude here. This frequency will be multiplied by this amplitude, which is higher, of course. This one will be good, will be higher, of course, and so on. And here smaller. So the amplifier will actually act as a filter. It will decrease some frequencies and amplify some frequencies. The noise, as I said, all amplifiers have upper limit and lower limit, F1 and F2. Okay, but not all of them they have F1. The amplifier without F1 amplifies signals all the way down to 0. Then if you don't have F1, this means that you amplify starting from DC. Even DC will be amplified. Okay. F1 is caused usually, this F1, we create it usually by a capacitor at the input. Capacitor at the input to suppress the DC. And F2 usually is created by capacitor at the output to block or suppress the DC. What is the signal to noise ratio? Signal to noise ratio is very important factor. This is the ratio between the signal itself, the desired signal, and the noise included in the signal. So for example, if the signal is, the amplitude of the signal is 10, and the noise, it has a noise that has amplitude 2, then the signal to noise ratio is 10 divided by 2, which is 5, which is relatively high. But if, for example, and is relatively low, I mean, okay. But if the signal, for example, is 100 and the noise is 2, then you see 100 with respect to 2, of course, is good. It's 50 times. Okay, so you have a good signal. The noise is relatively small with respect to the noise. So the higher the signal to noise ratio, the better the signal. Which makes sense, of course. You don't need any noise, usually. Miller's theorem. This Miller's theorems, if we have amplifier that has a feedback, so you have amplifier like this, it is a negative amplification, so it is inverter. So V out supposed to be negative AV times Vn without this Z. So what if we have a feedback like this? Okay. So as you see here, some inverting amplifiers designs employ feedback impedance. Why? Okay. So it can shape the frequency response. So we design it to shape the frequency response. So this Miller theorem actually is replacing this one here with this one. So we remove this and find equivalent circuit for it. then in this case it will be easier for us to do, because all what you have to do, this is just input impedance here and this is output impedance. So we replace this Z by this input impedance and this output impedance. And as Miller says that this Zn Miller equal what? Equals this Z divided by A plus 1. A is this one here. Plus, of course, positive, the amplitude of it. Okay, so it is Z divided by A plus 1. And the output impedance equal A Z times A over A plus 1. And I say again, A is the absolute of this. Okay, and this is what's mentioned here. The proof is here. The proof is here. You can go through it. It's very simple way to do it. So, like for example, what is IN, for example, of Miller? If I want to calculate the input impedance, it is the voltage Vn divided by IN. So current, for example. Okay, what's IN? Is Vn minus V out over Z. You can calculate here. If this is very high impedance, it look like this. Okay. Then all what you have to do is just replace this V out by AV times AN. And then after that, you take VAN outside and find Zn Miller. But at the end, this is the ratio, this is the formula that we'll use to replace this one by its Miller equivalent circuit. So we have Zn Miller and Z out Miller. If we have a capacitor instead of inductor or instead of resistor, then it will be very similar. If it is just a resistor, then you just replace Z by R. Z by R. Here it is. Okay. If it is a capacitor, it will be a little bit different. So the minimum, the Cn Miller equal what? Equal C times A plus 1. Okay, this is C, remember, this is not Z. So this is not impedance, or this, and this is not in ohm, this is C in farad. So Cn equals C times A plus 1, and the output capacitance here is C times A plus 1 over A. Then all what you have to do is just substitute by this value to get the Miller equivalent circuit. The last part in this chapter is just some problems. For example, here, I want to calculate, I believe here, we need to calculate the voltage, the load voltage. I want to calculate this voltage. So how do I calculate the voltage? I can calculate or use this formula to calculate the amplitude, the amplification, A for the system, and then multiply it by the input. This will give you the output. So what's A system? A system is Zn, that is 1 mega. So 1 mega over 1 mega plus Z generator, which is 50 ohm. Of course, here you can neglect this one here. You can neglect 50 with respect to 1 mega. So you can say this is 1. Okay, so roughly it is 1 because Zn is 1 mega and Z generator is 50 ohm. So of course you can neglect. So this is 1. AV is what? AV is given here is 50. It is 50 time. So now it's 50 time what? Z load. What is Z load? Z load is 1000. 1000 over what? Over Z load plus Z out. 1000 plus 75. Okay, 75. You may neglect 75 with respect to 1000, but you can't. Okay, let's just use. Okay, so let us calculate it with neglecting this one, and I'm sure that we will get a very close number to this. This is the exact number. So okay, so it will be 1000 kilo ohm, which is 1 kilo ohm, divided by 1075. Z load and Z out. Okay, multiplied by 50. That's it. So what is this? 46.51. It's almost the same. Almost the same. Okay. I neglected this completely. This one completely. Why? Because the input impedance is 1 mega, which is very large with respect to Z generator. And then when you multiply this time, the input here, which is 10 millivolt, then this is the answer in millivolt, 465 millivolt. If the circuit of problem 1 has a compliance of 2 volt, okay, so this is a compliance, so this is the range, this is the allowable range. Will the output be clipped if, let us see here, What is the load? V load in this case is what? Is 465 millivolt. So actually it is less than half volt. Then it is less than the compliance. The compliance is 2. Okay, so if the output is 0.5, that's fine. So in this case, there's no clipping. But what if the input is not 10, like previous example was 10? Make it 100. If it is 100 milli, so 10, make it 100, you multiply it by 10. Then for sure you multiply the output also by what? By 10. So in this case, V load will be what? Will be this number times 10. Okay, so instead of 0.465 or 465 milli, will be 4,651. So it will be this number here, which is 4.651 volt. Okay, so you replace milli by volt. So now, according to this is supposed to be the output. The output is 4.65, which is more than 2. Then in this case, yes, it will be clipped. It will be clipped at what? At 2 volt. Okay, then the output will not be this number, but it will be 2 volt. Why? Because the compliance for this amplifier is 2. If we have amplifier with AV equal 25 and the input voltage is 20 milli, there is no load. Find the output signal to noise ratio if the amplifier generate an output noise range of 10 microvolt. So this is the output noise. The noise is 10 micro. Okay, so we have to compare it to the output signal. What is the output signal? The output signal will be AV times Vn. Because the amplifier, the input is 25, is 20 milli. The amplification is 25. Multiply them, then this will give you the output. 25 times 20 is 500 millivolt. Okay. Now compare this output to the noise, to this noise. So it will be 500 milli divided by 10 microvolt. Okay, you have to be careful. This is 10 micro and this is milli. Then what is this ratio? It is 50,000 to 1. Of course, this means very high. This means that you have a very good amplifier, very good, very high signal to noise ratio. This is about Miller equivalent resistance. So if, for example, AV is negative 20 and R 60K, so we need to replace this one here by this one. As I said before, all what you have to do is just substitute here to get the input impedance and here to get the output impedance. The input impedance will be what? Will be R, that's 60K, divided by magnitude of A is 20, negative 20, then it will be 20 plus 1. So it will be R over 20 plus 1. And here, it will be the same, but you multiply by A in the top here. You multiply everything by A. So let's calculate this. To see how we calculate it, it is just R, that is 60K, okay, divided by A plus 1, which is 21. So this is the input resistance here, 2.857 kilo ohm. And the output will be exactly the same, but you just multiply everything by what? By A. So we multiply this by A, which is 20. It will be 57.1. Here it is. This is the number, the output impedance. If you have capacitor, so AV is negative 30 and C is 200 picofarad. Then in this case, this is the input capacitance. This is the output capacitance. Okay. So what do you need to know to if you want to calculate the input capacitance? It is C, which is 200. Time what? Time A, which is 30 plus 1, that is 31. Remember that you are taking the amplitude of this one, absolute value. So times 31, which is 6.2. Okay, 6,200 picofarad, which is 6.2 microfarad. This is 6,200 picofarad. And then you multiply this by what? By, or divide it, sorry. You divide it by A. You see here, you have you divide everything by A. When you divide it by A, which is 30, So this is the answer in picofarad, 206 picofarad. Okay, or you can say it is 0.20667 microfarad. You can do that. Okay, it's up to you. I believe this is the last problem in this chapter. As I said, this is a very easy chapter. If you have any question about it, let me know in the live lecture. Thank you very much for watching, and see you in the next chapter.